So work, power and energy. So quick recap of the definitions we learned in the last lecture. We saw that work done by a constant force for F being a constant force. So by constant, we mean that it's a constant vector. So both magnitude and direction are constant. And the direction are fixed. In that case, we define work done as the dot product of force with displacement. So S is the displacement. And if the question arises whose displacement, then it is of the point at which force is acting. So whatever force at which whatever point at which the force is being applied, if it displaces by S, then the work done is the dot product of force and displacement. And therefore we can see that we can further simplify this as Fs cos theta, where these are the magnitudes of the force, the magnitude of the displacement. So in SI unit, it should be expressed in meters. Then the work done will be expressed in joules. And theta is the angle between the two vectors, force and displacement. So we saw that 1 joule is equal to 1 Newton meter. Okay, so that is the SI unit. So this was the first definition we saw last time. Okay, also erg is the Cgs unit of work. So 1 erg is equal to 1 dyne centimeter, which is the same thing as 10 raised power minus 5 joules. So that's the relationship between joules and ergs. However, we also saw a more general definition of work done, because a force need not always be constant. A force can be a variable force, either in terms of the magnitude of the force changing or in terms of the direction of the force changing. So in that case, we define work done using an integration, what is called the path integration. So that also becomes an important part of the definition. In fact, that, as I was telling you, is the general definition of work done, and this one is a more specific definition of work done, which can be understood from applying the special case of a force being constant to the more general definition of work done by any force, including variable force. Anyhow, so just a quick recap of this, and let me know if there's any question or any doubt related to this. Of course, we'll be doing a lot of application questions, so you'll be able to understand these things. Okay, now next let's come to the
One second.
okay.
Sir, we have to write all this.
No, we have written this down in the previous lecture, so just make sure you understand this as we're discussing the recap of this, right?
Okay,
It's
sir.
there in your previous lecture notes. So it's just a quick revision.
Sir, I didn't understand how to solve the integration method that last time we did. So can you just take a recap?
We'll look at more examples. Okay, so now let's look at the general definition of work done. So in general, if a force F is acting on or acting at a point, and as that force is acting, that point is displacing through a certain path, or it's moving through a certain path. So let us say this is the path or trajectory of a certain point, let's say P. So trajectory means path of a certain point P. And while that point P is moving, okay, there is a force F acting on it. So that force is continuously applied to that point. So we'll take the most general case that as we are applying this force, it might be, from point to point, it might be varying both in position, magnitude as well as in direction. So during that trajectory, if I take a small displacement, small part of it ds, and that is at an angle theta to the instantaneous force. So this is, let's say, at some time t. After some time, let's say the particle has come here, it's moved somewhere else at some time t plus delta t. So now the same force has a different magnitude, let's say, and a different direction. So you can see this vector is different to this, both in magnitude as well as direction. And it's making some different angle, therefore, with the displacement. So how to define the work done in the entire path, let's say, starting from this end A to this bend B, to this point B. So the work done, it is defined as the path integration of F from A to B. And what we mean by path integration is that it is F dot ds is integration from the initial point A to the final point. So this will be the work done by this force, while the point at which the force is applied is displacing from the point A to B. So W is the work done by a force F acting at a point P while it displaces from the point A to B. So this is the general definition. Okay, so here F may be variable or may even be constant, because this is the general definition. So if it's variable, it may be that either or both magnitude and direction may be variable. So this is the general definition of work done by any force. Okay. So yes, as of now, you first just understand the definition, and then we'll see how this can be applied at different situations. So the definition is something like this, that because the force is a variable, we cannot directly use F dot S, because while the whole displacement from A to B is happening, so during that entire interval of time, the force is not remaining constant. So if we directly calculate F dot S, what will we substitute as F? Because F is not constant, F is variable. Hence, we cannot use that definition of F dot S. So instead of that, when the force is variable, what we do is the entire journey of the object, or the journey of the point at which the force is acting from A to B, we chop that journey. Okay, so if this is the entire path, we chop it up into small little segments. So each segment is a displacement ds. Now, even though the force might be varying, but ds is a small displacement, so it will take very less amount of time for ds to happen. So during that small amount of time, there's hardly going to be any change in the force. Now, whatever the force was when the particle was here, by the time the displacement ds has been completed, we can treat the force as a constant for that small interval of time. Of course, if we compare this force with that later time when the particle is here, the force might have changed significantly. But during that small displacement, the force has not changed. So during that small displacement, for that small part of the journey, the work done will be a very small amount because the displacement is small, but that work done will be F dot ds. Okay. So therefore, for the entire journey, what will be the work done? It will be the sum of dw, the work done for each of these small displacements, right from the initial position to the final position. So that's how this becomes integration, because it becomes, we want to sum up the work done by all these, at all these small positions of all these small displacements. So that summing up is actually calculated by the method of integration. Okay, is this point somewhat more clear now?
Sir,
Yes,
why did we integrate that?
because the force is not constant, beta. So because the force is variable now, in general, we cannot take the formula F dot S, because while that total displacement S is happening, in between the force is changing from point to point. You understanding my point?
Sir, so whatever the answer will be, the
Yes.
work done will be for a particular point or the whole journey?
No, so that the difference is, see, for if I've broken my journey from here to here, okay, from this point A to this point B, if I've chopped that total path into small little displacements ds. So for a particular small displacement ds, how much is the work done? The work done is only this much, F dot ds. It is not integration, it is F dot ds alone. Is this point clear firstly?
Yes, sir.
So this is the same displacement definition as we saw earlier, F dot S, but the difference is instead of the total displacement ds, here we are taking only a very small part of the displacement, which is ds. And because we are taking a very tiny part of the displacement, so it's for a very small interval of time. So in that interval of time, we can treat the force to be constant, and it has the instantaneous value F. Okay.
Okay,
So
sir.
so for that very small time dt in which the displacement is ds, so for that small interval, the work done is this much. So now for the whole interval from A to B, what will be the work done? So for that, we have to sum up the F dot ds for this displacement, then this displacement, like this, starting from A all the way to B. So that summation only is the process of integration. Understood this point? No?
Yes, sir. Yes.
Okay, so that is why we have to ultimately calculate, we have to do the integration of F dot ds for the work done in the whole journey. Because F dot ds alone is not giving us for the whole journey. It is just giving us for a very small displacement ds, which is a part of the entire journey. So now for each of those ds's, which together add up to the journey, we have to add up the work done. So that is where the integration process comes in. Okay, so hope this point is fully clear now. Okay, so we'll start with a couple of more examples of how this is implemented. But before that, let us also note down the important thing that in this formula itself, F dot ds integration, if we treat force to be a constant, if force becomes a constant, then in that case, this formula automatically simplifies and it becomes F dot S. So in the above formula itself, for this W is equal to integration F dot ds, if we take a special case where F is constant, then it will imply that integration F dot ds will simply become, because F is a constant, so it's dot product with integration ds, and integration ds will be nothing but the total displacement. So we are back to the earlier formula we had seen. This is a special case for work done when force is constant. So this special formula, which is a simplified version of the integration, that it is F dot S, this can be shown from the general formula also, but by applying the special condition that the force is constant. So when the force is constant, integration of F dot ds itself becomes F dot S. All right, so hope this is also clear now. So let us look at some examples of work done by force. Okay, so let us take the somewhat simplified example of an object sliding down an inclined plane, but this time it's a rough inclined plane. So let's say theta is equal to 30 degrees. Placed a block of mass m. So m is 10 kilograms. G is 10 meters per second square. And the coefficient of friction mu is 1 by 2 root 3. Okay. Whereas theta is equal to 30 degrees. So first of all, draw a free body diagram and show all the forces acting on the block. Then calculate the work done by each of these forces. As the block slides down the incline through, let's say, 20 meters. So as the block slides from here to, let's say, here, through a displacement of 20 meters, you have to calculate the work done by each of the forces. So start with this question, people make a free body diagram to show all the forces. And when I say show all the forces, that means you should be able to show the direction and magnitude of each and every force which is acting on the body. And once you've done that, then we will calculate the work done by these forces by using the definition of work done above. Okay, so let's check out the free body diagram. Hope you people are trying to work this out. Got the free body diagram correct at least by now. Okay, very good, Rishita, that's correct. The values are correct, okay, of the forces. Now all you have to do is, you have got the forces correctly, which means that obviously you've got the directions of the forces also correctly in the diagram. Now you have to find the work done by each of these forces. So for that, what you need to do, you need to find the dot product with what? With the displacement for each of the forces, right? So in total, how many forces are acting on this body?
3.
4.
Forces, right? Weight,
Component 4.
weight, normal reaction, and friction. And friction will be which type of friction? Kinetic friction, because it will start sliding. You can see that mu is less than tan theta. There will be kinetic friction of mu n acting like this. This angle will be theta, the same as this angle here. So the forces acting are 3 in number. Mg, which is of magnitude, how much? 100 kg. Okay. Normal reaction, which is of magnitude mg cos theta. So 50 root 3, so newtons here. Mass was 10 kg. So okay. So normal reaction is this much. Okay. And friction mu n, so that will become 25 newtons. Okay. So one thing the FBD is showing you here, that the block is going to accelerate like this. Okay. Now to calculate work done by the forces, we need to understand which definition of work done will be applicable over here. Can you tell me which of the two definitions we have studied we should apply over here for work done by each of the forces? Are the forces variable or are they constant?
Constant.
All three of them are constant, correct? While the block is moving. So if this angle is 30 degrees, you can see here this angle will be 60 degrees. Okay. So for each of the forces, we'll have to use the formula work done is equal to F dot S. Use this because F is constant in the case of each one of them. So in the case of work done by the gravitational force, how much that will become? That will become mgs into cos of which angle? Now the angle between gravitational force and displacement is this angle here, which is 60 degrees. So this will be cos 60. So it will be 100 into the displacement of 20 meters. Okay. This is 100 newtons, but into cos of 60 degrees. So the work done by gravitational force, or mg, will be 1000 joules. Do a work of
Sir, one question, sir.
yes.
Sir, so now when we have to find work done by every force, do we have to find of each components also, like mg, sin theta, and everything?
No, better, because see, components में आप divide करोगे तो फिर separately each component's work done you will have to calculate, and then add them to calculate the work done by that particular force. So why we will do that? That's not necessary, no? Like we could have broken mg into two components, like mg sin theta and mg cos theta, separately calculated the work done because of the parallel component and perpendicular component. But the net work done, we'd have to add the two, no?
Yes, sir. Okay, sir. Got it.
No, got it. So that's not necessary here. We will directly use the formula or directly use the definition that for a constant force, the work done is simply dot product of force and displacement. So it becomes like this. Okay. Now, what about work done by normal reaction?
0.
Yes, very good. That is
0.
correct. Very good. Because normal reaction is perpendicular to the displacement. You can see that over here. This angle is 90 degrees. Okay. So cos theta is equal to 0. Oh. So, okay. Whereas what type of work friction is doing now? How much?
Sir, opposing the
So it's going to do what? Negative work done. Very good. The work done by friction, when we calculate, will become magnitude of friction into S into cos of 180 degrees when we solve the dot product. Okay, because you can see this angle is 180. So the magnitude of friction was 25 newtons. The displacement is 20 meter, but so friction will end up doing a work of minus 500 joules. Okay. Now, after some time, we will come back to this question itself when we are discussing the relationship between kinetic energy and work done, and we'll observe something important over here. But for the moment, we are done with this question. Okay, we'll refer to this data again after some time, but calculated the work done by each of the forces. So this is all that was necessary over here. So we've actually just seen one aspect of this chapter in this question, and that is calculation of work done by a constant force by the dot product. We've applied it for 3 different forces. That's a different matter, but we've just seen the execution of that one formula, dot product of force and displacement. Okay. Now let's take another example where we come to our more general definition of work done.
So sir, 1 second, I was just noting that down. 1 minute,
Okay.
please. So no, like a little bit scroll down, please. Thank you.
Scroll down further. Okay. But this is the last of it, work done by friction. Okay, done.
Sir, almost 1 second.
Okay.
Okay, sir, done.
Okay. So next example, we'll see a situation where we have to apply the general definition of work done we were talking about earlier. So we have this smooth horizontal surface. And on that we have placed a block. Certain mass. Now we start pushing it with a force like this, which is a variable force. So now let us say this is our x-axis. Okay. And this point is our origin. And initially the block is at x equal to x1. And after some time, the block under the action of this force has reached x equal to x2. Now the force F, it acts horizontally. It is along the x-axis. Okay. And is variable such that the magnitude of this force is, let's say, magnitude of this force is alpha upon x square, where alpha is a constant. Let's take some value. It is 20 Newton meters square, and x is the position, okay, or x coordinate, okay, in meters. We can see that this is a variable force now. Okay. So we have to calculate the work done by this force for the movement of the block or the displacement, whatever, from x1, which is, let's say, 1 meter, to x2, which is, let's say, 5 meter. So as the block is displaced from the coordinate of 1 meter to the coordinate of 5 meter under the action of this type of a force which is varying with the x coordinate such that it's inversely proportional to x square. So we have to calculate what will be the work done by this force while the block is displaced from x1 to x2, given the values of x1 and x2 in meters. So this is now an example where we will have to apply the general definition of work done by the integration method, because the force is variable. So just try this out, people.
Sir, 16 joules. Sure.
Sir, are you there? Sir?
Hello, sir. Sir, can you hear us? Hello.
सर आए क्या?
नहीं नहीं
नहीं,
सर EF के हो गए लगता है।
मैंने सर को कॉल करने का ट्राई किया बट वो पिकअप नहीं कर रहे हैं।
प्रशांत आला.
जोगिंदर हरा भाई जोगिंदर इन खेतों में इतना हक देगा
हरा भाई जोगिंदर इतना ही मीटिंग करेगा.
दुकान पे बाल कटवाने के लिए, वहां से कंगा उड़ा लाया चुपचाप। क्यों जोगिंदर? अरे भाई जोगिंदर इतने मस्त हेयर स्टाइल करेगा इस कंगे से, इतने बाल खड़े करूंगा जाल लगा लगा के इस कंगे से, सीना सोची नहीं होगी। दोस्तों मेरा नाम जोगिंदर। जोगिंदर शराब भाई, जोगिंदर आ गया है दूध, और इस पतीली का सारा दूध पी जाऊंगा एक सांस में। इस लॉकडाउन में इतना दूध पी जाऊंगा सोची नहीं होगी।
सच्चा रहोगे किसी ने?
थारा भाई जोगिंदर इतनी तेज गाड़ी भगा देगा, इतनी तेज गाड़ी भगा देगा किसी ने सोची नहीं होगी। जो ओ जोगिंदर, थारा भाई जोगिंदर इतना नाच लेगा, इतना नाच लेगा, इतना डांस कर दूंगा, इतना बटाई बट कर दूंगा, डीजे वाले ने सोची ना होगी। उठते ही मेरे अंदर भाई यार हिम्मत चाहे गरम गरम
You can just unmute and speak to me.
Okay. Students, sorry, there was some disruption, some internet issue at my end. I think most of the participants have left the meeting, so we will continue this lecture on a different date, people. Okay. If you have done this question, let me just confirm the answers for you.